I am running one lecture behind my announced titles. So I was not able to finish what I was trying to cover in the last lecture, which is actually the main topic of all these discussions. So I'll finish that and then I'll do binaries. So the main thing I want to cover in this lecture is the field theory aspect of G. So I'll try to argue that, well, so far we have seen the standard classical way of calculating gravitational waves from slow sources, fast sources, which give you memory and so on. Now I'll argue that it's easier to do things in if you use field theory. And by field theory, what I will mean is that I'll mainly talk about graviton as a quantum field and rest of the object as classical fields. So I will not talk about, so I'll treat graviton emission from stars as the vertex where you have a, so this is your T mu nu, which represents your binary star, and you have a graviton, H mu nu. So this is a classical current, and here, since it's produced, so this graviton will be treated like a quantum field. So what that means is that you can imagine loops of gravitons, so you can imagine things of this nature, but there will be no loops of the classical object, the current. Okay, so we start with H mu nu is, G mu nu is eta mu nu plus kappa H mu nu, and as I said last time that when you treat this as a quantum field, you want a canonical kinetic term for H mu nu, so you need to have this, and it's kappa is 32 pi g square root, and it's easy to see why that should be, because you start, let's say, with 1 upon 16 pi g r. Okay, linearize it. What you'll get is 1 upon 16 pi g, and this will give you half H mu nu box H mu nu. So what you have to do is, instead of H mu nu here, so this was the metric, dimensionless metric. Which I was showing last time, right? This was when I expanded G mu nu is equal to eta mu nu plus H mu nu. So this is what I was doing last time. You would have got this, but what you have to do is you have to expand with a kappa so that you absorb this 32 pi g there. So in terms of, so let me just to differentiate, let me call it tilde here. So if you make this, this will go to H tilde box H tilde. Well, so we will do the calculations with this H tilde. So normally I will not keep writing tilde. I'll assume that you know that in the context whether we are talking about the quantum field or the classical this thing. And sometimes at the end of the calculation for the quantum field, we will want to extract what is the gravitational wave. So then we will have to stick in a kappa. Okay. So if you have H mu nu is equal to something A, then H mu nu would be kappa A. Okay. All right. So the gauge symmetry here is X mu going to, and H mu nu goes to Okay. Now, what we do is we expand the matter Lagrangian, which is a function of etc. in. Yes, please.
So we don't know quantization of gravity.
No.
Yeah. So how can we do this thing and be sure that? I know that the results match, but is there?
So what we are doing is that if we avoid a loop,
Yes.
okay, then as you were saying the other day, that a tree-level Lagrangian is not actually giving you anything quantum. It's just a language.
We should have, in some sense, we should definitely have loops.
Yeah, so when you have a loop, so the thing is you have to show a need where you have a loop for your actual observable. So for instance, I calculate in Newton's law, and you can see these papers of Donoghue. So they expand these vertices, propagators, except in powers of h bar, and they show that this object is 0th order in h bar. So although we are actually calculating a quantum process, I mean a Feynman diagram, but it's actually a tree-level process we are calculating. But if you try to calculate something like, okay, this is very small. So, and it's also divergent, and you cannot absorb these divergences in counter terms. That was the problem. But this lecture I'll tell you, there will be a process where you will actually need a loop in an observable. So that comes from this memory theorem. So that's the interest in why the memory theorems are interesting, because you will come across a process where you will have to involve a loop of the graviton for consistency. And then you have to argue, well, does it prove that gravitons have to have loops or things like that? Okay, so expand G mu nu in kappa h mu nu. So this is your delta h mu nu, kappa. So what you do is you do okay, and we already know that the derivative, functional derivative of the action is just the stress tensor. So this will give you actually okay. So the extra term that you get, which is proportional to, and this is just kappa. So you will get a Lagrangian from this. So the interaction Lagrangian for h mu nu, you can read off from there. If you write G mu nu as kappa h mu nu, will be kappa by 2. Okay, and this is no matter what type of matter there is, because it's okay. So this is universal, because you are taking the functional derivative of the action, and that's always the stress tensor. So this is universal for all matter. Coupling for all fields. And these fields also include graviton fields. So at some point, if you expand it to the third order and write the T mu nu of the gravitons, then this will give you a graviton-graviton coupling with the same kappa. Okay. Then we have the symmetry. So if you want this invariant Li invariant under xi mu. So what you do is, when you have this, replace h mu by that h mu plus those extra terms, you will get, I'll write it here. So Li, so delta Li will be something like kappa by 2 p mu nu d mu xi nu plus, when you make a transformation. And you want these extra terms to vanish, which means you integrate by parts, and this will give you etc. And this means that you want del mu t mu nu to be 0. So invariance under that symmetry means that your action, your t mu nu has to be of this form. Now this is a bit different from what you have in classical gravity. So in classical gravity, you have this Einstein's equation, which is g mu nu is equal to some constant times t mu nu, right? This is so this is right. And if you operate a covariant derivative on g mu nu and you write out all the terms, expand all the terms with the Christoffel connections, they'll all cancel. So it's an algebraic identity, which is that this gives you 0. So this is called a Bianchi identity. Okay. So, but here, this means that, so left hand side means 0, means this is 0. So in GR, this is the quantity, this is the conservation of stress tensor. Whereas in linearized GR, we will just take this to be the conserved quantity. Okay. So they will, so what that means is that if you calculate it, you will get a partial derivative plus terms which are quadratic in h mu nu, not linear. Okay. So we'll, that can be checked perhaps. Okay. Yeah. Yeah. Kappa by 2 is not a dimensionless quantity. It is, kappa is, so sir, roughly this is 1 upon Planck mass. So it's a dimensional quantity. G is 1 upon Planck mass square. So it's a small number. So this is the energy, and if the rest of the interactions are some energy units, it will be some energy divided by the Planck mass. So any interaction which has a smaller energy than Planck mass will have a very small contribution in the amplitude. So that's the, okay. So now I'll so I'll assume you know the some field theory. I mean, I'll just use the basics, not too much. So I'll just introduce the terms and then we'll go on. So now have a, supposing this is a quantum field. So you have to write it in terms of, I'll just write, this is the polarization. I'll just write down and then I'll explain what. So what I've done is I've written the field in terms of this polarization tensor and a creation and annihilation operator. These are annihilation on A lambda is annihilation and this is a creation. So this you should interpret as an operator which annihilates a gravitational wave of polarization lambda. And similarly this creates a graviton of polarization lambda. And these polarization vectors just depend upon the direction of the graviton. So these have various, so the first thing is that you can now start treating AK, A dagger, sorry, this is so these are have commutation relation just like your scalar field, which are, and this is a completeness relation which is this is some projection operator whose form I'll okay, yeah. So this is a linearized gravity where the gravity is now treated as a quantum field. So linearized quantum theory. Okay, so the nonlinear effects will be important where there the intensity of the graviton is very large. So for instance, when the black holes are merging, then h mu where h mu is no longer less than 1, the field is no longer less than 1. Also the metric is not less than 1, they are the nonlinear. So then you are talking about many gravitons. So then this theory will not work. Yeah, up till the merger this will give you, I will show you that up till the merger this gives you the correct waveforms. I mean we have calculated for elliptical orbit, hyperbolic orbit, but at the merger this does not bring. Huh?
We get the right one in the inspiral phase.
So there are two types of inspiral we'll just study. One is this pulsars which are, those for that this works perfectly. And in the in the black hole mergers, this will, just at the time when this stops, this, they draw a line where the merger happens and then there is a, so that point, towards that point it will stop.
It's still the inspiral phase.
Yeah, this is the inspiral phase. So I think the distance is that when they are 6 Rg, the merger is supposed to happen. So this is where it will break down. 6 Schwarzschild radii between the two black holes, this will not work anymore. Okay.
So this is three-level calculation, but in principle you can include the non-linearities of the...
See, this is I'm still giving you a Lagrangian. Then you can do any calculation. And when you are doing the calculation, at that point you should decide whether a tree level will work or I will have to have extra terms.
No, I mean, if you're at least, because of geometry problem, etc., at least tree level is where you would expect it to work, right? Tree level, what I'm asking is whether the T-mu that you're defining here, is it in principle can we incorporate, let's say, higher relative corrections of gravity or something like that?
In the T-mu nu.
So if you can take this to the right hand side and incorporate that.
Yes, you can, so you have a point here that you can start with this theory and make loops of gravitons and write it as an effective theory, where you have this plus R mu nu. So what you do is you have a T mu nu of the, let's say,
matter loops basically.
But then this will be R mu nu alpha beta, let's say, of H mu nu H alpha beta. So let's say you are talking about a black hole. So first you have the mass of the black hole which is radiating. Okay. Then you have the field of the graviton which radiates, which can be written as R mu nu. Yeah. So that can
that's in the last part of your lecture yesterday.
Yeah.
You had similar thing.
Yeah. So that was by hand, but you can write it in the Lagrangian. So that was just taking the T mu nu and writing one process. But you can do it systematically by expanding this. So if you want to do it, what you do is you expand this in a mid background. And then you have to, when you do this in the background, then when you do the expansion, all these things will come where this is a background and that's the fluctuation. And you can write out systematically then. So then you can, if you, in those theories, you can treat the black hole mergers better.
So, but also that kind of means that you need to know the metric G value for the coalescing black hole. So
Yes. Yes.
That's probably already like a problem.
Yeah. So that is the question of back reaction. That if you have a background metric and it stays like that, then you can write this term. But when it is radiating, actually the background changes. When it's radiating, so then the back reaction will not be included in this. So that will be the problem. So if you have a small energy radiated from an intense graviton in this background, then this will be okay. But if you have a merger where the
regime is this approximation is valid.
This one.
In this linearized, where linearized tree-level graviton calculations can be used for making predictions about gravitational waves, classical gravitational waves.
Yeah.
Because that's, I think, the goal. Right?
That's the goal, yes.
So, for instance, the last setup that you were saying yesterday, where there is a huge amount of energy is radiated into the gravitational field, where is this calculation useful?
Yes. So what happens, look, let's say you have two gravitons, which are black holes, which are merging, okay? And they are emitting gravitational waves. So this, which collapses to form a black hole, okay? If you calculate what's happening inside there, then this will not work. But what we are doing is we are taking the H mu nu, which we are actually observing, so which have gone out of the black hole Schwarzschild radii, and we are saying that you take these guys and then calculate the gravitons which are emitted from these guys. There this works perfectly.
So it's not the total gravitational wave output that you're concerned with. You're basically looking at the final, let's say, small fluctuations and asymptotic regions.
Correct, yeah. So what will reach the asymptotic region where you can, so in all of these things, we are looking not at observers who are sitting here, but an observer who's sitting at an asymptotic region where the gravitational wave will reach. Okay. So I'll explain. So what that means is that when you draw, I'll show you in a couple of minutes, that when you have a propagator, we will no longer draw a Feynman propagator. We will have a what's called a retarded propagator. That is, it's causal, that it's only one way in time. But when you have a close-by object and you are talking about virtual processes, then you have a Feynman propagator, retarded and advanced together. So that's the okay. Good. So now I get to the soft graviton theorem, and I see this YouTube keeps throwing up these lectures, and I see mine also. There are many lectures on the soft gravitons. So what I'll do is just the basic amount, and my main aim is to tell you that the applications here. So basically I'll derive the soft graviton theorem for the first two steps, including the log terms, believe it or not, and then where are these applied? So these are applied in situations, for instance, if you have this jets from GRB, or you have a black hole, another black hole has a hyperbolic encounter, and So this will have a gravitational emission, this will have a gravitational emission. So hyperbolic scattering. Hyperbolic here doesn't mean exaggerated, it means it's the orbit is a hyperbola. So in these cases you will get what's the memory term, and it's very simple to calculate this from the soft theorems. So that will be our aim, that the application of soft theorems to calculate the memory terms. Okay. So I think I have some space here. So let's write so given the action, I can write my interaction vertex, Li will be so this will be my interaction vertex, right? In the quantum theory, when I want to write a Feynman diagram. No, it is epsilon. So just like the photon, J mu times the epsilon mu, and that's your this is the interaction vertex. And if I want to, so I have two particles P1, P2, and I have a graviton emission, then this vertex is with more space here. Li for this is K. So that's your stress tensor for a body of mass m, classical object of mass m. Okay. So now I get to the soft theorem. So the idea is that supposing a scattering takes place, two stars pass by each other, or there is a in spiral one star another, then calculate the process. Let's say the amplitude for this process is n. So there are 1, 2, 3, n particles here. Okay. Then calculate a different process where so you have a graviton emission from each of these one by one. Consider one at a time. Okay. So let me call it PA, okay, and K. So this will be written as minus kappa by 2 epsilon mu nu star lambda times. So I'll just write down the answer and I'll argue why that should be. So when I want to write this process, so all I do is I've created a new vertex and a new propagator, okay, in this old diagram. So the vertex is this factor times the T mu nu. So let me write the T mu nu. The T mu nu is so this is the same particle PA, okay, which is going through, and plus I don't keep terms of the order of k square, so I'll just keep the leading order, okay, and this will be divided by the propagator. The propagator here is, so the momentum here is PA plus K, and K goes out and PA remains. So this is PA plus K whole square minus m square. Okay. So this is, sorry, So this is the,
So this is coming from some PA plus K type thing.
this one.
No, the upper, the numerator.
This one is just coming from this T mu nu.
Yeah, but it contains a P plus K type of thing. And that
Yeah, it is a P2 is a P plus K, which I'm ignoring the K. So I'm ignoring the K in the numerator but not in the denominator, because denominator it's a pole. So I'll in the end take K equal to 0. So I'll ignore the K terms in the numerator but keep it in the denominator. And then this times your existing amplitude, An. Right? So this is, I shouldn't write it like kappa if this is, you can expand this PA, so this I should write it as MA square. This is PA square, is cancels with MA square, K square is 0, I'll treat it like a real graviton, so that leaves you with this. Okay. So this was actually, this will give me, I should write this as n plus 1. So the amplitude for this n plus 1 process is the amplitude for the nth process hard scattering multiplied by a kinematic factor. So I'll write it again here. PA mu. So this I should have, so I did that for one particle, so I should write it as a summation. This can be for all the particles in those legs, so I'll do a summation over A, right? Okay. So this is my leading order, what's called the soft graviton result. Okay. So how do you interpret this? So to, okay. So this kind of thing you have seen before when you do in practice, when you do, for instance, let's say you have a nucleus, so Za, Z protons, and you have electron, low energy electron scattering from this, and there is a bremsstrahlung. Okay. So this part of the thing you treat it as An, and that is your my extra P1 to P2 process. So when you do this, what you do is the amplitude for the electron scattering, you just keep this part and you treat An as 1 here. So what that means is that, assuming that this scattering has taken place, the probability amplitude for a graviton emission is given by that. Okay. So this, if I write, this is amplitude for h mu nu emission times amplitude for n scattering. So first an n particle scattering takes place, then n graviton is emitted. But if you already know that this is a classical process when a scattering has taken place, you can take this part to be 1, and this then gives you the graviton emission. So then your is that's all. Okay. How do I write the numerator? So what you do is you take, I have taken this P1 and P2 and sorry. So in this process, for instance, you write P plus K as my incoming and P as outgoing and K as a graviton, and use the formula which I wrote for P1, P2, where P1 you can write P plus K and then you take K to 0. Okay, I wrote the T mu nu for a P1 to P2 process. Okay. Okay, so so the remaining thing that needs to be proved is that if you have this, if the K, so this is a proof. I mean, what is left out is this process.
I'm talking about this line that so this A plus 1 is proportional to A.
Yeah.
So in theory you can prove this for the soft code.
But here this is just one of the.
This is the proof.
It's a diagrammatic proof. There is no.
This is the diagrammatic proof. There is.
It's a diagrammatic factorize it.
At tree level, factorization is kind of trivial in some sense, right? Because you are just taking.
At first few orders it's very trivial. What is left in the proof? There is a loophole here, which is that this is a complex process. I didn't say that this is a point scattering. This is some. Okay. So supposing this leaves out things like a graviton coming from an internal line. Okay. So then you have to show that the graviton coming out from an internal line is a subdominant. It doesn't give you a pole. So only this kind of factor, external line, gives you a pole. Okay. So that part I left out. One can look up the proof. Thank you. So you have to show that internal line emissions don't give pole. And
But at least strictly speaking, that term would be not a tree-level term.
no, the point is that this n process need not be a tree level thing. It can be anything.
That's what I'm saying.
Yeah.
So, but if you're working fully at tree level, this is automatically.
Yeah, yeah.
No, but in tree level, if you have this cross term, then by definition the emission is there.
Yeah, this is,
So this is sort of like internal brainstorm. Right?
yeah, this can be,
No, but I'm saying that like that term, unless there is a vertex function there, that is just a standard tree-level process. That process you can just read off from 5 and 9. So
Yeah.
in that sense, it is just an extra factor.
yeah. But the thing is, this proof is more general than that.
Yeah.
That this works even if it's any complex process where there are internal loops. If you have so basically you have to write the propagator and write a Q plus that propagator and show that this doesn't give you a pole in K. That's actually not so difficult to show, but you can leave it. So graviton from an external leg gives you a pole. That's the message. Okay. Okay, so then I said that this is my amplitude. So in quantum fields, what's an amplitude? An amplitude is, I have Li, I have 0 here and 0 graviton and 1 graviton, and this is my, that's what an amplitude means. So this is what you have calculated.
So I think the thing that I guess Weinberg proved is the point that Ranjan was worried about. Otherwise, it's a very trivial statement.
Yeah. I guess, yeah. Exactly. What Weinberg proved was that the internal lines, but the internal lines are not that difficult.
But at least it's not.
Yeah. This is a very trivial thing. That if you have a propagator, internal loop, let's say you have this process. Okay, and I am talking about graviton emission here. But you can have a graviton emission here, but it is a propagator. This does not give you a pole in the Q, in the graviton momentum. So if you write a propagator and take Q square equal to 0, you can show that. Yeah, but it's the proof.
I think that's the reason it's called Weinberg's of graviton.
No, Weinberg actually did a lot more than that. He said that if you add all orders, I was going to come to that later. If you add all orders, okay, then it becomes exponential. So he did, So he did that one graviton, then two gravitons and so on. And then he did something more interesting where you had a loop of gravity. I'll come to that. I'll not jump ahead. So he said that the collinear terms cancel the loops. That was the thing. This block North stick.
That's the place where you are saying that the loop plays a role even though it is...
Yes, that's the place where I'm saying the loop plays a role. There is a cancellation in the tree level forward scattering. But
I was just saying that it has the name of somebody in the theorem. So it cannot be...
Yeah. So Weinberg exponentiated it. He did it all orders. But many other people also have done this similar thing. Okay. So Weinberg did something interesting which you can play with. So what he did was, he said, let this kappa be dependent on the particle. So I'll put a kappa here. Kappa is a function of A, so it's not universal. Okay? And then he said that K mu of this process, an plus 1, should be 0. It's the water entity from that symmetry. And then you'll see that when you put K equal to 0, you'll get a P dot Q here, which should cancel by a P dot Q. So you can see this. PA dot PA. Okay. And I have a kappa A here. Okay, so this is lambda with, right? So I multiply this with a K mu. Okay. So then this will give me just kappa A PA because K dot P will cancel with the denominator, right? And then he says that we also have a PA nu equal to 0. The energy is conserved. So he says if you have this statement and that this should be 0. So these two statements will prove that kappa has to come out. So kappa is universal. So that was, so this is the equivalence principle. What? Say it loudly. Yeah, so this is that gauge invariance of electrodynamics. So he also proved that E is the same for all. Similar thing in...
Actually, this proof is for the electrodynamics version. I think the other version will have a quadratic term, right?
Same thing. This is the graviton.
Is it a graviton?
PA in the electron, this thing, the numerator will have only one term. See, J.
So what will be the confused?
Okay. So there the coupling is J mu A mu. Okay. The soft theorem will be E summation the epsilon mu times J mu. So let's take J mu. So this will, I'll call it E times P mu. A mu. Charge times the momentum is your classical current. Okay. So this will be then P mu. And the story about the propagator is the same. The propagator will be, this is A. Okay. So this is the QED version.
So this is the soft factor for QED.
This is the soft factor.
This one is quadratic.
This is quadratic, yeah. Yes. PA nu. So this is quadratic in P, that is linear in P. So there is a, then.
So basically just because there's no P at all sum, it is just P equal to E plus sum of everything. The total charge has to be conserved.
Total charge has to be conserved. So if you take EA here, then if you apply with the K, K mu to this, you will get cancellation here, so you will basically get EA is equal to 0. So the total charge going in and coming out should be 0. So this is charge conservation. So in electrodynamics, that's charge conservation, and in gravity, that gave you the equivalence theorem that kappa is universal for everything. Okay, so I was at this point. I'll keep this. I can erase maybe.
The right side.
Okay. So as I was saying, the amplitude means 0 to I, this thing. So where does this come from? You write this Li as a h mu nu. There is a dagger in h mu nu. That part will give you 1. Right? So from that you can read off what is the effective T mu nu. So this A lambda can be interpreted as epsilon minus I So this is just that amplitude.
That epsilon mu, I think you mean epsilon mu, right? There, on that top photo.
Software.
There's an epsilon mu, epsilon mu, right? I just want to show. Yeah, above. PVD.
Ah, sorry, very sorry, yes. I just meant epsilon mu, that goes in. Yeah. So then this is, I'll interpret that. So that amplitude, I'll interpret it as an interaction. Interaction means there is some polarization term times the T mu nu. So the effective T mu nu that I read from there is basically this. So that is a kappa by 2. Okay, that's my T mu nu, which I read off from the soft theorems, from a scattering which has happened. Now you see, this is something which I derived last time. If you take PA, which is gamma times MA VA, okay, and I'll write this P dot K, I'll pull out this is EA and K naught minus I'll pull out so K divided by K naught is the n, the direction of the graviton. PA upon EA is just the VA. And so let me write this. Can I erase this part? I think I can erase this part now. And EA, I will write it as gamma MA. VA dot. Okay. So write this all out. you will see that this will give you m square, which will cancel with the denominator m. Then there will be a gamma square in the numerator, which will cancel with 1 gamma here. So in the end, you are left with t. So I'll write that ij part, which is what is used usually. Tij is gamma k naught vai b. So this is the factor I had from my Linearized Wishart potentials. Look at the moving charges. But you can see that this was very trivial using that amplitude method. Okay. All right. So one more thing we learn here is, given that this is my Tij, okay, this is coming from a scattering amplitude. What is, so this scattering amplitude is happening here, and I'm an observer sitting here. What will be the field? Am I out of time already? I'm going really slow. I have what? 50. That much? No, it's okay. I mean, I have a lot. I thought that I'm at the end of my 1 hour is over. So I want to calculate my h mu nu at rt here from my t mu amplitude calculation here from the soft theorem. So the answer is, which I will derive, 4g by r. Okay, and so I'll write the dk naught upon 2 pi and this is actually my this part. So this is my Tij in momentum space, right? So what that means is that I calculated this, but this is in momentum space and I want this in position space. So then I have something like this. So let me derive that in a. But if I do that, I want to show you what this really means. So the point of this discussion was, this is k omega. This was a momentum space calculation where there is 1 by k naught still left. Okay. What does this k naught do? The Fourier transform dk naught upon 2 pi, if there is no other k naught factor, is just the theta function of the retarded time. Okay. So assuming that this is the formula, which I'll show you later, a pole in Tij, pole in K0 in Tij implies a step function in the GW signal. Okay. So in the position space, what you will get is that this will be 4g by r times this factor times this is epsilon ij. So if you do this integral of a 1 by k naught Fourier transform, you'll get a theta function in time. Okay, so that's how you relate the theta function with the calculations from the soft theorems with a pole gives you a step function in space-time signal. Okay. Okay, so I have done. Okay, so now let me derive this thing, where it's a you calculate a t mu nu in this space, and you want your h mu nu in the position space at a large distance, and you are not assuming that these are slow moving objects. Okay, we have to drop that assumption. So let me give you so I've done this. So again we'll start with the Green's function. So we want so I can write this in a covariant way also, and as I said later that you can write this in a covariant form, but in the end what matters is the transverse stressless versus projection of this ij. So but x prime. Okay, and this one in the this is where this is the scalar Green's function. And this projection operator, this actually needs to be derived by inverting the full Lagrangian, but I'll just not do all that. Is half no, this is mu alpha nu beta plus mu beta nu alpha minus eta mu nu eta beta. And this also turns out to be the sum of the and when do you need this? You need this when you take an amplitude and you square it. So you have an amplitude a lambda which is epsilon mu nu t mu nu, and you want to square it and sum over the polarizations. Then you need terms like you will get this term, and then you use that projection operator. So this is
so that was needed for cross sections.
For what?
For cross sections.
Yeah, for probabilities. Yeah.
So one more question. So this calculation that you're about to do, the analog of this, I don't think we did yesterday. Right?
Well, yesterday what we did was we calculated Tij in the x space and just used the Green's function and calculated h for slow and fast objects. So what I've done is now I have a Tij in the momentum space, and I still want my x in the position space at distance. Okay, so then this sort of a
basically the goal will be to get the quadrupole radiation.
actually I'll do a more general now. The quadrupole was for slow moving objects.
Yeah.
Now I'll do the second one, the Linearized Weishart.
But I thought Linearized is already here.
Yeah, this is, I have to derive this. This is what I didn't derive.
Oh, I see. So you're trying to basically derive this?
Yeah, I'm deriving this. I just, see,
I'm a little confused. So I thought that this expression that you wrote was directly why is this not right?
No, so this I gave you the Tij in momentum space. Okay, then from the Tij in momentum space, I want the h in position space at a distance r.
So, but that T mu nu, so is that T mu nu that you're trying to derive? I mean, because that T mu nu will imply this side, right?
Yeah, that T mu nu is exactly this.
Yeah. So
But from that T mu nu, I want, so what does that give you? This gives you amplitude for emitting a graviton.
sure.
Now I want what is the value of that graviton field at a large distance r. So I need to propagate it.
Basically, you want to compute this.
So I want to derive this in the sense that T mu nu times a propagator will give me h mu nu, and that propagator is exactly that, which I'm going to derive.
I cannot.
Yeah.
Oh, I see. That's the part.
Yeah, that's the part. The propagator will give me this times 1 by r usual way. So maybe I should not have written it before, but this needs to be derived.
So the thing in the bracket is parenthesis is what we already have.
Exactly. Correct. So the thing is, this is what we already have, and I want to show you that in the momentum space you have the thing, then how to derive it in the position. Okay. Actually, okay. So let me clear the board and oops. I'll keep this. And this, as I already wrote, is the projections time the scalar function. And for the scalar function, I'll use the retarded Green's function. Let me write it down. So then I have calculated. Okay, so first I will do is, I will so let me write T mu nu x prime as d4k upon times tilde okay, and this is the thing I derived, the momentum space. Okay, so I will first do that. I'll just insert that there. Then the Green's function g alpha beta will be times the retarded Green's function, and for the retarded Green's function I already have this form, minus 1 upon 4 pi t prime minus t. So the t prime is the source time and t is the observer time. Similarly, x prime is the source, where the source location, x is the observer location. And this thing here, you can also rewrite it as delta of x minus x prime minus t minus t prime. Okay. So what does this? This is also the same way of writing this. This tells you that with x is greater than x prime, that means source is distant, then t has to be greater than t prime. Okay, so this is true for t greater than t prime, otherwise it doesn't. So that is why this is a retarded propagator. Okay. So what does that tell you? Basically, that given a amplitude, supposing I want to calculate a scattering. So I have another object near, I want to scatter a graviton. Okay. If it is a close object, okay, then I will use a Feynman propagator. That means I have a virtual graviton exchange. Whereas I want to actually see this as a real graviton, in that case I use a retarded Green's function. Okay, that's a okay. So now with this, I think I can. The algebra is quite simple here. Okay, so what you have to do is insert this thing over here. Okay, and then one more thing I need to do. I want to write this, the scalar part of the thing, x minus x prime, as x plus x prime by r dot n, where and sorry, the other way. Okay, so this is the direction of the source. So these are three vectors. And so I'm treating it as a distance source, and what I do is in the time part I t minus okay, so in the time part, in the x minus x prime, I insert the full thing. And in the 1 by x prime, I insert this one, I insert only 1 by x. Then, so as I said, this I am assuming that t prime is not small compared to x prime. That means this can be relativistic. But, so this is true for fast moving. So, insert this Green's function there, okay, do the t prime integral. So there is a x prime, t prime, do the t prime integral, there is a t prime inside this, there is one t prime here. When you write this in the momentum space, replace that t prime by this guy here. Okay, so I'm skipped the step, I will written the step, but okay. So replace the t prime here by these guys, okay, then you will get x prime in the exponential, right? In this, replace this t prime by t minus, you will get a x prime dot n term, and there is already a x prime dot k term. Now do the x prime integral, d cubed x prime integral. Okay, so I'll write it down just so that you don't forget. So after t prime integral, you will get d cube x prime e to the power I k minus k naught n dot x prime. So this came after that t prime integral, and do this will give me 2 pi cubed delta cubed k minus k naught n. This will give me a delta function in k, and this is actually, so you still have this, do the d cubed k integral after that and get rid of this delta function. Is everybody confused? It's actually so trivial that I don't want to write it, but I can if you want. Should I write this? Try it and take a picture of this sheet later, or okay, I'll write it. Sometimes, oops. So what did I write? Okay. I'll do this. So my h alpha beta is equal to cup eight pi r So in this, all I have done is 1 by x prime dot x I have taken to be for that 1 by r. Okay. Now do the t prime integral. So then what I will get is so t prime integral means I'll just replace this t prime with this t minus r, and I'll collect terms in and I'll get minus I theorem t minus r So I got this k naught dot x term from the t integral. There x is. And now do the so then that factor just gives me okay. So we are right. Okay. Then do the d cubed k integral. So what that will tell you is wherever there is a k, that's only here, will get replaced by k naught n. Okay. So then that replaces k goes to k naught n. And then finally you will get okay, so so in the end you will get h alpha beta is 8 pi r times, this is still left. The k naught integral you did not do. And in the mu nu, you replace the k by k naught n and k naught. So the e to the power minus I k naught T minus R. So this is the expression I promised, except for this pesky factors here. So what do we do here? This is the, what we have done is, this is the metric, quantum field. Okay. Whereas what we want is the metric. So the metric H alpha beta is kappa times field. So you multiply another kappa there. So then basically, so I'll write it here itself. So the metric, the field is, and that's, if you expand, is just 4G by R. Okay, so this is the formula I was, and now you can see that this basically is your T mu nu, I mean, this is the same as your, or I write Ij, just take the Ij, made this thing. And I can write this whole thing as Tij in the X. This actually just will be a function of T minus R. Okay. Because this is just, this whole thing is the Fourier transform of the Tij in the position space. Okay. So, so this formula actually just tells you that you can calculate this from your amplitudes and then stick it in this formula to get the gravitational wave at a distance. So let me just write this full formula properly. dk naught upon 2 pi, and if I want Tij Tt, this will reduce to my old lambda ij kl tkl k naught n k naught e to the power T minus R. Okay, so this is the message, and I think I'll just quickly show you now a hyperbolic orbit full calculation. So, okay, let me complete this discussion. So this, although I did not derive it, this soft theorem I said n plus 1 of some PA Q here, or PA K, let's say. This is S1. So, as far as I know, there are 3 terms known yet, and the first one I derived, which is so this one I derived. So this is 0th order in K, but you can write in first order and second order in K, and those are the angular momentum So you have to involve the first order in angular momentum, and in the second order in k, and divided by, and in the second order in k, what you will get is k alpha, k beta, so these are various orders expansions in k. So this is actually these things one can derive not by calculating diagrams, but by writing, supposing you write the most general term, first order in k beta, okay, and where you use the conservation equations. So k dot the amplitude is 0. Okay. Then this is the unique form if you use only the conserved quantities to. So here J is your conserved angular momentum of your external particles, or the PA, just like this was the moment of PA and so on. So this is done in various books, my book also, so you can look it up. It's tedious but not impossible. But there is one interesting thing. So these are the extra log terms. So did Lada derive that? Ashok Sen's log terms? You guys were saying? No. Okay. So he mentioned some log terms, right? Huh? Yeah. Lada gave. Yeah. So what is interesting, so when we are looking at soft theorems, I was saying that soft theorems are interesting when you look at the zero momentum and you have some poles, because the remaining terms are subdominant. So there are two types of pole. One is that 1 by omega pole, which gives you the step function. Another pole which was derived by Ashok Sen and Lada and Sahu and collaborators are of the form where you have a log of omega. Okay. So he derived it from the diagrams, but I am going to derive this. I mean, I'll not derive it on the board, but I'll show you how that derivation works. And in this kind of thing, you'll see that this power law expansions are actually, trivial if you calculate the full diagram instead of perturbative. So let me show you how that works. Yeah. Last time. Yes, so last time what I was doing was, I was considering this Tij in the position space. Now I said that I have a Tij which is a function of momenta. So then how do I calculate my Hij in position space? So I should write here T and R. Okay. Yes. So I extracted this from my quantum field, and then I said I use a retarded propagator to get my classical field at a distance. Okay. So in the end, I'm actually calculating a classical object. If I was taking a nearby this thing, I used a Feynman propagator. Then I would have got the H alpha beta, which is a off-shell particle. That means scattering something else. But we are interested in this classical object. Okay. Okay, so I will do a quick calculation, or I'll just show you the outline of a. So I have some notes about this block Nordsdick, but I'll skip that. If there is a time, I will come back to that. So I will do hyperbolic orbit, and as I promised that. And before I move on, I should say that these are of practical use, this sort factors, for calculating things from jets, and where it can be a if you want the dependence on the spin of the object, you use the second order and calculate using this the amplitude, the Tij, using the sort theorem and calculating the signal. Okay. So now I will talk about binary or so there are two types which are used, where is the elliptical. So it's a conic section where epsilon is smaller than 1. This is the eccentricity. And hyperbolic, where the eccentricity is greater than 1. So this is of application in the merger calculations, where you want to calculate the signal from the mergers. And this is of interest where let's say you have in the center of the galaxy, you have a black hole of 10 to the 6 million 10 to the 6 solar masses, and around it you have many stars and black holes which are orbiting at very close encounters, which have a hyperbolic orbit, and you are looking for GR from here. And what is of interest in this is that this will give you a memory signal. Okay, this hyperbolic orbit will give you a memory signal. This will give you, of course, also give you a memory signal from the graviton, as I said last time, the nonlinear memory. So let me do this or this one, and then show that methods are the same for the other one. Okay. So in all these calculations, what we need is so supposing I want in the momentum space, this is simply 4g by r t of omega, and this omega is what I was calling k0, the graviton frequency. Okay, so which means that I want to directly do the momentum space calculation without doing this integral over omega and getting the time. So in a hyperbolic orbit, you think of it as, you can reduce it to one particle motion around the center of mass, and the particle will have a mass which is m1, m2. So the orbit can be reduced in terms of a single particle effective motion, and that also works if you have a heavy particle here and light particle going around. Then if the heavy particle doesn't move, and it's effectively a single particle motion with whatever is the mass of mass mu. Okay. So in the hyperbolic orbit, okay, I'll write the full trajectory. So I'll start with writing in let's say xy plane. So where xi is a parameter, I'll just write it down and explain what these are. And here xi parameter, this goes from 0 to infinity, I think. So, this is a parametric form of a hyperbolic orbit in a xy plane. So, there is no z motion. So, this is how x, y and t move. And here this omega is what's called the fundamental frequency. So, basically, this one has no single frequency. It will be a sum of this omega naught. Okay. So, because the velocity is not a constant as it moves, so in the frequency space, it will have many frequencies, which will be harmonics of this fundamental frequency, as you will see. Okay. So, for this, I'll just give you the outline now. I will not. So, we are looking.
Is this a generalistic solution? Is it a geodesic solution?
So, this is of linear order in. You are asking if there are V by C corrections to this orbit.
No, I'm just saying that.
This is the Newtonian solution. This is the Newtonian solution. So, does it accommodate fast particles? You have to think about that.
This galaxy center probably you don't need that.
Galactic center, you don't need that. But this gives you a velocity which is close to 1 from which you get the memory signal. So you are using relativistic objects, but with this. So this I shouldn't say something wrong. But these are Newtonian orbit. So I think what Newtonian orbit means is that you are still in the linear h mu nu, and I think it also means v small 1, right? Yeah. So v, if it becomes 1, this should break down. Yes. Yeah, clearly it should break down when v becomes 1. So this is probably okay for stars. They are not really like going at the speed of light. They are. Yeah. So this works okay for big black holes black holes going around this supermassive black holes, but it will not work for like a neutrino or a light deflection. Okay. So basically then what you have to do is calculate Txx, let's say, at k and the frequency and so this is the definition of my x mu nu, t mu nu, the velocity times the mass, velocity square times the mass. And all I am doing is that this is now a function of xi, that means the function of t, okay? And I want the thing in the momentum space. So I'll just remove because the position part k is a dependent variable. K is n omega. So it's enough to do the time part for this calculation. Okay. So then what you do, and similarly t xy, t yy omega and Txy is similarly so now the thing is use that change t to xi, change the variable and do this integral in the xi variable. So that's a lot of algebra, but it's algebra. I mean, it's just 19th century maths. So in the end, I will not give you the full answer. I mean, I will not give you the calculation. I will give you just the answer. And all these things which I am doing right now, you can look up the details in a paper with Arpan Hayat, Suraj Prakash, and I. So this is in 2024. So you can look up all the details there. So this TXX turns out to be mu nu. I'll explain what is nu. Omega naught a square. That a in the orbit is what is called the, when I wrote a, that is your semi-major axis. And so this a is that semi-major axis, pi times we get Hankel functions. Prime means derivative with respect to the argument of this in nu. So this nu is the whatever is of this Bessel function. Is this the order or this is what? So this is, this is the order of the Bessel. Sorry, of the Hankel function. So this one, and there are two Hankel functions, kind 1, kind 2, and this is the order of the. Okay, so this turns out that, and similarly for Tx, Tyy and Txy. Having calculated this, then my Hxx, if I want in the position but in the frequency, so at a large distance but in the frequency domain, this is just 4g by r times Txx, that whatever I've written there, omega. So this, and this nu is actually turns out that this is the harmonic so this nu is the frequency. As I said, that it doesn't have a single frequency. There is a frequency defined by that this one, which is the fundamental frequency, but you will actually have a combination of harmonics. So this is a function of nu, which is ratio of the actual frequency divided by the harmonic frequency. Okay, so this is a variable in frequency, and having calculated this, that one is just the 4g by r in momentum space. Now I am looking for, let me look for, once I have calculated this laboriously for this and this, I am going to look for the zero frequency limit. Okay, so what is the, and this is the frequency space. What? Or in this case, you can take it as nu equal to zero limit of this calculation. Okay. So what we get is something interesting. So then I will get terms of the kind which is omega inverse Aij, which are regular in omega, plus Bij log of omega, or you can just write it as log of omega. Okay, so these are the pole terms. Remaining becomes 0 when omega goes to 0. So having the full expression, I can extract the pole terms, and so I can just give you the so what I'm doing is, let's say I have Hij in general. I take the zero frequency limit. Okay, I have a term which is 1 by omega, and whatever coefficient I get, call it Aij, and I'll get something with log omega which I call Bij. So this Ai and Bij are contained in that if I just do that expansion. Okay, and so I'll write one, and you can Hxx is 4G by R to okay, I think I'll get something of this kind. Did I get a, yeah, here we have a log term, and I'll write down one more expression where Hxy is 4G by R times something times there is a log omega E by omega naught minus and so there are two terms H. So there are terms which are poles in omega, and then there are terms which have only, poles in log omega. And you can look up these expressions in our paper. This is fully there. Okay, and then you'll be curious to know that this is the same thing that is done in a memory calculation. Okay, because what is it done in memory calculation? Let's say you have a single particle scattering. This is particle of mu scatters of a center of force. Okay, so there is a particle going in and a particle going out. So this is of the form Pa, this kind of thing. And then there are log terms, log of k. Okay, and this is the 1 by omega term, and there are log terms. So we calculated in this paper, what we did was in the scattering calculations, what you do is you take these asymptotic states. Okay, you only the momenta and in the initial state of the initial and the final state. So you can convert that momenta to linear momenta. Supposing you have a particle here and it goes like that. Okay, it has an impact parameter b and a velocity v. These are what is experimentally measured of a hyperbolic orbit. This v times b, this is the angular momentum, and total energy is half mu. So this is mu vb, mu v square. So if you have an initial particle moving with the velocity v, it has a conserved energy and this, where v is the initial energy, velocity. Of course, velocity changes, but this E and L remain same. Okay, so you can actually write this scattering terms in terms of these conserved quantities, and you can actually translate this formula into that, which we did in our paper, how to translate this linear momenta into this orbital parameters. And what we find is that there is this paper, Sahu and Sen, and I had some consultation with Sen and Sahu where there are some corrections made to our paper actually, and then finally what we found was that this calculation which comes from this full orbit, this matches the log terms in the hyperbolic calculation. So the summary of the thing is that what does these soft theorems get you? The soft theorems are power law in omega, right? This omega, omega square and so on. But if you know only the asymptotic states, P1, P2, the scattering states. So you have not solved, from the initial states you can do the full orbit as power of Q square. So without having to calculate the orbit, you can calculate the amplitudes. Whereas if you calculate an orbit and just do a simple orbital calculation and then expand in Q square, you should get the same thing, which we explicitly see that we do. Okay, so that was the and I think I'll just say one thing about this Bloch-Nordsdick, and no, I'll say one more thing, one more line, and there's one more thing which is interesting in this field theory calculation is that you want to calculate the energy emitted in either an elliptical orbit or a hyperbolic this thing. You use the field theory expression. So I have this is T mu nu, H mu nu, kappa by 2. So in this process is happening, and I know the structure of T mu nu as an orbit. Okay, then this is just the and use the mod square. So I'll call it so omega is the graviton frequency and omega prime is the T mu nu frequency, which is summed over. And there is an integral over this. So that calculation of T mu nu, stick in here, square it, you have this epsilon mu nu square, use the completeness relation, do all the algebra, and in the end you will get a sum, and this will turn out to be, so if I calculate the power in a frequency interval, it kappa square upon 40, some function of the eccentricity. So this is a known function of eccentricity. It comes out something like that. And this matches the standard calculation. So you can do the calculation in the frequency, in the momentum space, things which are also calculated in the usual thing. And one more interesting thing here is that, so I have now my power, let me call this power, which is energy radiated in a particular frequency range. Okay, and I want to plot power as a frequency, PW in the frequency range. So I'll get something depending upon E. E is, let's say 1.8, 1, etc. Okay. So notice that this is omega equal to 0. So this power radiated at 0 frequency is actually not 0. Okay. So this is the power radiated. So that you can take the full power expression and get the 0 frequency limit, and you will see this. So in the 0 frequency limit, it is basically 32 So this is the full expression. So basically this is the power in your memory signal, which is easy to calculate. Once you calculate the Tij in the momentum space, rest is, the thing is very trivial. Okay. So can I have 5 minutes to say something about block nodes check, or I can say this next time? It's okay. I can say it next time. All right. Thank you. No, actually we have calculated, so they are assuming asymptotic in state, asymptotic out state, and they are saying doesn't matter where the actual trajectory goes.
Yeah, but I'm saying in your calculation.
In our calculation we know the full trajectory.
Right, but the full trajectory goes into the calculation because the omega is, you have this stress tensor in omega space.
Correct, yeah.
And you Fourier transform, and the Fourier transform tracks the entire curve.
Yes.
That's the reason.
Correct, yes. So once we have the input of the full trajectory, it is in the Fourier space equivalent to all power expansion in the frequency. So there is a more general, the memory theorem doesn't say that from asymptotic states you can tell a lot, independent of what is the interaction. But we are saying that, okay, as a cross check, when we actually know one interaction, you can check that it actually gives you the same answer. So this actually, our calculation shows it that for one example it works, the matching works.
The fact that it is Newtonian or not, it doesn't matter.
It didn't seem to matter here, yes. There in the Newtonian calculation, still this 1 by omega was there. So yeah, that's something actually one should check where.
Because their calculation is in some sense, it's more general in some ways, but less detailed in some ways. Like less detailed in the sense that it's not much for a. So you have.
Yeah, I can do that for all powers of Q, not,
Explicit formulas.
Exactly, yeah. Okay, so the other thing is, this is actually the full signal. You calculate the full signal and then you can extract the memory part by taking the limits. So we are whereas that soft theorems only give you the pulse, the memory thing. It doesn't give you the full signal. So in that sense, this is more general. Okay, so I will stop here and then I'll Monday this time. Thank you.